So Alex Kasegi is a technical sales engineer. In this role, she helps customers identify quantum use cases in their organization. She teaches our virtual training class, and she supports customers as they adopt the DWave technology. Prior to this role, Alex was part of the DWave support team, where she supported all parts of the technology stack, from installing quantum processors to helping customers with their research and application development. Alex earned a Bachelor of Electrical Engineering at the University of Victoria. So with that, Alex, welcome.
Thanks for the introduction, Susan. And thanks to everyone else for joining today and taking this hour out of your day. This webinar is on quantum programming with hybrid solvers, and we'll be really focusing on the constrained quadratic model solver, or the CQM, as we call it. There we go. So today we're going to talk about, well, really briefly, I'll introduce our technology stack and our hybrid solvers in general. Then we'll talk about a few use cases that are really well suited for the CQM solver. After that, we'll dive into an example called distributed computing. So with that, we'll do the problem formulation, and then we'll learn how to actually program the problem using Ocean. After that, I'll give you a very quick leap tour just to get into the distributed computing code example, and we'll open it up in the Leap IDE and actually run it live so you can see it in action. After that, I'll outline some next steps in case you want to continue learning, and then we'll have that Q&A period that Susan mentioned. But again, Tanvi and David are available as panelists, so they're also available to answer your questions. So please feel free to ask in the Q&A chat as we go. All right, so in case anybody's new to DWave, I just wanted to introduce who we are at a high level. We are the only independent quantum computing company that is a full stack technology provider. So that means we build and deliver the systems like Advantage, the cloud services like Leap, and the application development tools like Ocean. We also have professional services to support end-to-end quantum computing, to support the end-to-end quantum computing journey for enterprises and developers. On the system side, we currently provide access to quantum annealers, but we do have a roadmap towards gate. So in the next couple of years or so, you can expect to be able to access both quantum annealers and gate model quantum computers through Leap. Right now, Advantage is our quantum computer though. And Advantage has over 5,000 qubits, as well as 15-way connectivity between those qubits. So it's allowing us to solve more complex problems than we've ever been able to solve before. On the cloud side, Leap is our cloud platform, and it provides immediate access to Advantage and to our hybrid solvers. It also hosts resources such as documentation and code examples, an online Leap IDE, which we'll see a little bit later, and it also provides access to a vibrant community of quantum developers. So hybrid solvers use quantum and classical resources to solve larger business-sized problems. And this is really useful because the quantum computer, although it has a lot of qubits, it isn't quite large enough yet to be able to solve business-sized problems on its own. So that's why we've developed a suite of hybrid solvers to do so. The first hybrid solver that we developed is the binary quadratic model solver. And it works with binary variables. So variables can take on a value of 0 or 1, and it can support up to 1 million variables. Now we found that with this solver, as much as there was a lot of uptake, we also learned that not all business problems can easily be mapped solely to binary variables. So with that, we expanded into a new problem domain, and we developed the discrete quadratic model solver. So the discrete quadratic model solver supports discrete variables. So like on the slide, a discrete variable can choose a value from a set of numbers as one example, It can also choose a value from a set of strings or colors. It's really up to the user to define what those discrete values are. Now, both the BQM and DQM solvers solve unconstrained problems. So that means that constraints have to be formulated as a penalty model, and then they have to be added to the objective function. This also means that we have to weight the constraints with something called the Lagrange parameter, and it's a little bit of a process to tune that Lagrange parameter in order to get good results. It also turns out that most real-world problems have constraints, and that tuning an unconstrained model can prove to be quite time-consuming and quite costly. So with that, we developed our constrained quadratic model solver. It natively handles linear and quadratic equality and inequality constraints, and it also does the Lagrange parameter tuning automatically. So that part is now abstracted from the user, and you can spend more time just formulating your problem and getting it running on a hybrid solver quickly. We also developed new ocean tools along with the CQM solver that makes it more intuitive and easier to represent a mathematical formulation in the code. And in addition, the CQM solver supports binary and integer variables. So again, we're continuing to extend into new problem types. Now, one question you may ask yourself is, when should you use each of these solvers? And I put this table together to try to show some of the differences between them in terms of problem size, but also in terms of the types of variables and constraints that are naturally supported. So in the CQM column, it should be evident that anytime you're dealing with constrained problems, the CQM solver tends to be a better fit. Now, if you do naturally have an unconstrained binary problem, then it's a good idea to explore the BQM solver. Okay, with that, let's talk about a few use cases. Over the past couple of years, we've seen a few different verticals bubble up. So those are financial services, scheduling and logistics, manufacturing and mobility, and life sciences and materials discovery. There's also been interest in other industries like telco, the energy sector, and others, but we found a lot more uptake and more immediate ROI in these four verticals right off the bat. So on this slide here, we have a few of the brands that we've worked with. I'm going to go into a little bit more detail on the BBVA application and the Volkswagen application, because both of these they're really well-suited problems for CQM. And since those applications were kind of released by those companies, we've developed code examples to highlight how you might approach solving an application like that with the CQM solver. So BBVA, Bankia, and Multiverse joined together to look at the dynamic portfolio optimization problem. So for this problem, the goal is to find an optimal trading trajectory for an investment portfolio of assets over a period of time. In other words, the goal is to maximize the return of a portfolio given a fixed risk. And in this case, they also considered transaction costs. So they looked at a few different solvers that were classical, quantum, and quantum inspired. So on the classical side of things, they looked at Gecko and exhaustive. On the quantum side of things, they looked at IBM Q's variational quantum eigensolver, and they also built their own VQE that was constrained and constructed for this particular problem that was also backed by IBM Q. They, of course, looked at DWave. So for this application, they used the DQM solver. And then they considered a quantum-inspired tensor network as well. So in order to test out all of these different solvers, they used different size problem inputs that ranged from really small problems up to what they classified as extra, extra large problems. And they found that for the extra, extra large problems, only DWave's DQM hybrid solver and the tensor network could handle that size of problem. They also found that DQM achieved higher overall returns in 171 seconds, whereas the tensor network took a day to run. So they saw higher overall returns in a faster time with DQM. And if you check out LEAP in our code examples, you'll see an example of a portfolio optimization problem that's actually been implemented with both DQM and CQM solvers. Now, Volkswagen explored an application that has a direct impact to their supply chain. It's the multi-car paint shop problem. And in their manufacturing facility, car bodies of different models move through a paint line prior to assembly. So each body needs to be painted a base color, which is either black or white, before it's painted its top coat, which is a different color. They don't necessarily know what order cars will come in or how many of each model will come down the assembly line. But in this particular study, what they did know is that they needed to have 50% white cars and 50% black cars for every model. That means that as the cars come down, they need to kind of track what cars of what models have been painted what color. And then they need to swap out the color in the paint line to adjust to make sure that they maintain that 50% kind of status between black and white cars. So this is a challenging problem and can lead to a lot of inefficiencies because every time the paint lines are switched from black to white or vice versa, it increases the time that it takes to run the assembly line. It generates waste because the paint lines have to be flushed, and it generally increases costs all around. So the research team at Volkswagen designed an algorithm for the quantum annealer specifically to optimize color switches. And they looked at a run of 758 cars, where when they compared their current approach, they found that Volkswagen typically changes the color 288 times. When they ran it through with this quantum algorithm that they developed, they were able to reduce the number of color changes down to 57. So initially, what that meant was that they would be able to paint an average of 2.6 cars in between color swaps, but then when they looked at the quantum algorithm, they were able to increase that to 13.3 cars per color swap. So that was a large cost saving and time saving for them. And if you take a look at LEAP, you'll notice that we have a paint shop optimization code example that we've modified to fit for the CQM solver too. Okay, now that we've looked at what hybrid solvers are and looked at some use cases, let's take a look at this example of distributed computing. So for distributed computing, typically you have a really large application that is too big to just run on a single compute resource. So instead, what you need to do is break up this application into tasks and then distribute those tasks across different compute resources. So you end up having kind of a set of compute resources that are all working together to either compute a large problem or perform an application or whatever else you may be doing. So when we're dividing up the tasks and assigning them to compute resources, one thing that we need to be careful of is not to split up tasks that have dependencies on each other. So for example, in this kind of middle column here, we have tasks that are numbered in these boxes, and we have lines between them that indicate there's a dependency. So here, perhaps task 1's input depends on task 0's output. So we don't necessarily want to assign task 0 to one compute resource and task 1 to a different compute resource, because now the compute resources need to pass a message back and forth before task 1 can execute. So overall, when breaking up these tasks and assigning them, we want to try to minimize the number of messages that are passed in between compute resources, as it's a lot quicker to kind of keep inputs and outputs in memory and process tasks that are related within a single compute resource. So when we want to use a hybrid solver to solve this, we need to start kind of reframing this problem and thinking about it in a way that will help us build our model. So to reframe this problem, I'm going to think about this overall application and the tasks within it as a graph. So here on the top right, I have a graph with red nodes. The red nodes represent operations or tasks, and the gray lines between them represent dependencies between those two nodes. The goal is to assign nodes to partitions or to compute resources such that we minimize the number of edges that occur between partitions. So as you can see in this bottom figure here. You may notice, especially when we look at the bottom figure, that this is just a graph partitioning example. So we can continue reframing and think about this problem in terms of an objective and constraints. So for this problem, our objective is going to be to minimize the edges between partitions, or minimize the messages passed between compute resources. Our constraints are that we need every node in the original graph to be assigned to exactly one partition. So we don't want to assign a node to more than one partition because we just want the task to be executed once. And the other constraint is that we want to evenly distribute the load across all of the compute resources that we have available. So what that means, well, in this example, is that we're going to assign the same number of nodes to every partition. So partitions are going to be the same size. All right, now that we know what our objective and constraints are, we can start kind of building up the problem formulation. And the first step in that is to define the decision variables that we're going to use. So since my decision is which task to assign to which partition, I'm going to use binary variables called ik. So here the I is going to refer to a node and k is going to refer to a partition. What this means is I'll need to have a binary variable for each operation in each partition. So for example, if I have 4 partitions, then, and let's say I have task A, I'm going to have 4 binary variables for task A. So I'll have a binary variable for task A being in partition 1, task A being in partition 2, and etc. And whichever binary variable is equal to 1 tells me which partition task A will go to. So setting up the problem like this will give me a total number of binary variables equal to the number of nodes in the graph times the number of partitions. All right, now we're going to build our objective function. So remember that our objective is to minimize the edges between partitions. And the way we're going to think about building this is by building a penalty model. So I'm going to start thinking about this by just considering 2 operations, operation I and operation J, which are represented in these circles or nodes on the right-hand side here. And I'm going to think about 2 scenarios here. So in one scenario, node I and J are both assigned to the same partition. So we have one edge within the partition. We don't really care about that because it doesn't negatively impact our solution at all. In the second case, I'm going to assign node I and node J to different partitions. And you'll notice in this bottom image here that when I do that, I have an edge crossing between partitions. So it's these edges that we want to minimize. Another way of saying that is that when we have an edge like this that crosses partitions, we want to penalize this case. So we can represent these two scenarios by building a truth table, like on the left here. Now we have the first column, IK, which is going to tell me where, like whether or not node I is assigned to partition K. And likewise, the second column, JK, is going to tell me if node J is assigned to partition K. So in the first and the fourth row, you'll notice that IK and JK have the same value. So they're either both 0 or they're both 1. And what that means is that both nodes are going to be in the same partition. This is the case that we like, right? It doesn't negatively impact the objective at all. The other case though, so in rows 2 and 3, where one node is in partition K and the other node is not, this creates an edge that crosses partitions. And so this is a case that we want to penalize. We want to minimize the number of these cases. So to do that, we're going to introduce a cost or a penalty factor. And for rows 2 and 3, we're going to assign a penalty factor of 1 in order to make this scenario less favorable for the solver. So we increase the energy of that circumstance so that the solver doesn't want to choose that as much as it wants to choose the case where dependent nodes are in the same partition. So now that we have our penalty model, we can use this to solve a system of equations. And the equation that we're solving is just shown on the slide here. So A times xik plus B times xjk plus C times the quadratic term. And here, when we solve for A, B, and C, what we'll get is an equation that favors choosing a solution that has both dependent nodes in the same partition. Now we can then generalize this expression that we've built for 2 nodes. We can generalize it to the entire graph by just iterating over all of the edges and all of the partitions, which is shown by this double summation in the objective function equation here. All right, so now we have an objective function that describes this problem. We can now move on to formulating our constraints. So remember, the first constraint that we have is that we want to assign every node to exactly 1 partition. This is also called a one-hot constraint. And so the way we're going to represent this is for each node I, we want all of the variables for node I that have different partitions to equal 1. Essentially what this means is remember we have binary variables for each node and each partition. This will enforce the case that we only choose 1 partition for each node I. The second constraint is our partition size constraint. And remember here, we want every partition to have the same number of nodes. So what we're going to do is just count the number of nodes in each partition K and enforce that that is equal to the total number of nodes in the graph divided by the number of partitions that we have. All right, so now we have our fully formulated problem. So we have an objective function here, and we have 2 constraints. So now that we have our fully formulated problem, we have to choose which hybrid solver to use to solve it. And I'm going to go through why well, maybe not why, but I'll go through kind of the pros and cons for choosing each of the 3 hybrid solvers. So you can see why we arrive at the choice that we arrive at. So for the binary quadratic model solver, if we were to use that to solve this problem, what we'd have to do is expand out this objective function. We would also have to apply a little bit of a trick to each of these equality constraints to enforce them properly as penalty functions. After applying the trick, we'd have to kind of multiply out the entire expression, apply a Lagrange parameter to the constraints, and then we'd have to add the expanded expression of the constraints to the objective function, and then simplify all of the terms to end up with a set of linear terms and a set of quadratic terms that we can build a matrix from. So with the DQM solver, that's a lot of additional work. That means that arriving at this problem formulation here is really only just one small step to being able to solve the problem on the solver. Additionally, with the DQM solver, we have to tune the Lagrange parameter. So it isn't always immediately obvious what the Lagrange parameter value should be, and it often takes some tweaking in order to find that optimal range. And the last thing we have to do is do some pre-processing to determine whether or not the constraints were satisfied for the solutions that are returned. So again, there's a lot of steps before solving, and then there's also some work that we'd have to do after solving with the DQM solver. Likewise, if we chose to use the DQM solver, we would also have, a similar amount of work, but where we're winning out with the DQM solver is that we don't have to implement the one-hot constraint. So in order to use the DQM solver, we still have to expand the objective and expand the partition size constraint, but we don't have to worry about the one-hot. So that does save us a little bit of work. We still need to tune the Lagrange parameter though, and we also still need to do a post-processing step to determine if the constraints were satisfied or not for the solution that's returned. Okay, now if we choose to use the DQM solver instead, we're actually pretty close to being ready to submit our problem to the hybrid solver. So with the DQM solver, we can program the objective and constraints exactly as they are in that problem formulation slide or that summary slide. So as soon as we have the math equations, if we're working with equality or inequality constraints, then we're almost done. We can go directly to programming, and we don't have to do any other intermediary math steps. Also with the DQM solver, it has automatic Lagrange parameter tuning. So once we submit the problem, we don't have to worry about kind of tuning or tweaking the Lagrange parameter to get good results. The DQM solver will do that for us. And the last benefit of the DQM solver in this case is that when we get a sample set back from the solver, it'll tell us which constraints are satisfied and then which solutions are feasible. So a solution is only feasible if all of the constraints are satisfied. And so that saves us on the post-processing side of things as well. So we are going to choose to use the DQM solver for this problem. Okay, let's take a look now at how to program our objective and our constraints in Ocean. So we're going to start similar to how we started our problem formulation steps by defining our binary variables. So in Ocean, we now have this function called binary, and we're going to construct a matrix of these binary variables. You should also notice that the notation is very similar to the notation we used in the math equations. So we have x sub I p, where I is the node and p refers to the partition. So we're going to have one binary variable for every node and every partition. We also need to construct a CQM, so just an empty one to start. And we do that with either the constrained quadratic model function, or this can also be simplified to just CQM. Okay, so now we're going to look at how to build the objective. So this was our objective function, but in Ocean. So the way we're going to do that is start with an empty list, and we're going to add these terms for every set of edges and every partition to this list of edges, or to this list called min edges here. So for this objective, we can kind of map this equation directly to the code. Directly to the code. So you'll notice that this first summation here is represented as a for loop. So for ij and all of the edges in G, and that's exactly what this summation is doing. And then nested inside of that for loop, we're going to iterate through the partitions the same way that this second summation is doing in the equation. Then we can start appending terms to our list or building out the objective. And we can do that using a new feature in Ocean called symbolic math. So this allows us to just index that matrix of binary variables directly. So you'll notice that in the equation, we have xip plus xjp. And in the code, we also have something that looks very similar. xip plus xjp minus 2 times the quadratic term. So this is what I was referring to before about how CQM allows us to much more intuitively implement objectives and constraints. And this can really help speed up prototyping and application development. So the last step in building our objective is to sum up all of the terms that we've stored in this min edges list. And we can do that with the quick sum function that's provided in DyMod. It was written specifically to be more performant on summing up BQMs and quadratic models in general. So we sum everything up and call set objective on the CQM object to pass in the objective function to the CQM. Okay. Now we're going to look at the constraints. So for this one hot constraint, we actually have a function called add discrete on the CQM model that makes adding these one hot constraints very, very easy. So add discrete will take a list of variables or a set of variables that we just want to select one in. So for example, remember that for every node, I have a binary variable that corresponds to every partition. So I'm just going to pass in a list of those variables. So for a single node, the variable for each partition. And then add discrete will build the one hot constraint internally to make sure that it satisfies this equation here. So adding one hot constraints to the CQM model is also very easy and intuitive. Next, I'm going to add in the second constraint. So that was our partition size constraint. And here, remember, I'm just summing up all of the nodes in each partition and making sure that it's equal to the total number of nodes in the graph divided by the number of partitions. And here we're going to use the add constraint method. So we're going to first iterate through all of the partitions. And for every partition, we're going to add a constraint that sums up all of the nodes. So xip, that's all of the nodes in partition P, and sets that equal to, or requires that to be equal to the total number of nodes divided by K. Okay, so now let's take a quick look at Leap. Okay, I think that I am sharing my Leap dashboard now. I'm sure Susan will tell me if I'm not. Anyhow, so once you sign into Leap, this is where you land on the Leap dashboard, and you can access Leap just by Googling DWave Leap. I'm going to go directly to our code examples. And then I'm going to search for distributed computing. If you are interested in our portfolio optimization code example or the paint shop optimization code example, this is where you could come to search. So I'm just going to scroll down, and then I'm going to hover over this distributed computing card, and you'll notice that this button to load and Leap IDE pops up. So that's what I'm going to select. And now the online Leap IDE is starting up. So it's creating a virtual environment that comes with Ocean pre-installed, as well as some other common Python tools like NumPy that we usually use in conjunction with Ocean to develop models. The Leap IDE is also synced up with your Leap account. So your API token is pulled directly in, and there's no setup or configuration required to use the Leap IDE. All right. So when a code example opens up, it always opens up on the README here, but we've already gone through the gist of this code example. So I'm just going to open up demo.py, and there are a bunch of helper functions, but I'm going to scroll down to where we build the CQM. Okay. So we have this function for building the CQM. We're passing in a graph, and we're passing in the number of partitions k. Now you'll notice that as we look through this, this function, it's the same code that we looked at on the slides. So we start by building a CQM or an empty CQM, and then defining our binary variables. So here we're using v instead of x like we did in the slides, but it's the same thing. It's a matrix of binary variables. Next, we add the one-hot constraint using the add discrete function. Then we use the add constraint function to add the partition size constraint. And after that, we build the objective function and set the objective on the CQM, and then return the model. So again, quite intuitive once you have that mathematical formulation to build the CQM model. I'll also show you this down here where we call the sampler. So in this run CQM and collect solutions function, we're passing in the sampler, and I'll show you where we instantiate that. It's a little further down. But when we want to actually submit the CQM to the QCM Solver, we do that through this sample CQM function where we pass in the CQM, and here we've also specified a label for the problem. If I scroll down more past the processing, I can show you where we, yes, just right here. So this Leap hybrid CQM sampler function here is how we get access to the CQM hybrid sampler in Leap. And this is what we passed in to that other function, run CQM and collect solutions, and then use this sampler to submit the CQM. Okay, so I'm just going to run this demo now, just on its default settings. And you'll notice that it's printing out some information. It's already built the model, and it sent it to the Leap hybrid CQM sampler. And we get some information back as well. So it tells us how many nodes were allocated to each partition, how many links were between partitions, and how many links, well, average links were within each partition. So let's take a look. So we can also see what input graph was generated. So it's just a randomly generated input graph of 100 nodes. And then we can also see the output. So that input graph was partitioned into these 4 partitions that all have equal sizes and have minimized the number of edges between partitions. All right. I'm going to jump back now to the slides, because there are a couple other things that I just want to mention about CQM before we wrap up. So in that code example that we just looked at, we saw some information spit out in the command line about the problem or the solution to the problem. And we also got to see some nice charts to display the input and the output. What you get back from the solver, though, is a sample set. And for those of you who've used DWave before, you should be familiar with this. A sample set contains the values of all of the variables for each sample. So in this image here, each row corresponds to one sample. And this example here just uses 10 variables, just so everything would fit in the image. The sample set also returns the energy. So the energy is what we use to determine the quality of solution. A lower energy corresponds to a higher quality solution. We get the number of occurrences as well of each sample. And then what's new to the CQM solver is that we also get an array that shows which constraints were satisfied for every sample. And then the last column shows us if the sample itself is feasible. So for it to be feasible, all of the constraints need to be satisfied. And if we wanted to check which constraints were satisfied and which weren't for an infeasible solution, we can do this by using the isSatisfied array. But you'll notice at the bottom here, we also have some feasible solutions that are returned as well. All right, and the last thing I want to mention about using the CQM sampler is that it does have a tunable parameter, and that tunable parameter is the time limit. So for small problems, the default time limit is 5 seconds. If you wanted to increase that, this is how you do it. Just when you pass the CQM in, you can also specify the time limit. As your problem sizes grow, the time limit also scales. And as you work with larger size problems, the default time limit may not yield feasible results or as good of quality results. So for smaller problems, the default time limit tends to be more than enough to get good quality results. But as you start to scale, then we recommend playing around with the time limit to give the solver just more time to explore that energy landscape and arrive at a good quality feasible solution. So just a tip if you're working with larger problems on the CQM solver. Okay, so that wraps up the example. I did just want to point out a few resources and links to check out if you're interested in exploring this more. So the first step would be to sign up for LEAP. I showed you where code examples are, but that's a great place to check out the code examples mentioned today, as well as a number of others. I think we currently have 37 code examples available. We also have a resource library with resources to get started or learn more about the technology itself, ocean documentation, and if you have any use cases that you're curious about or are wondering if they're kind of worth exploring with our technology, then feel free to reach out to sales@dwavesys.com. And we'll be happy to have that discussion with you. I also wanted to mention that we just recently started a new kind of initiative. So we, this year, released this Quantum Quick Start training bundle. And that pairs our virtual training course, so it's a week-long virtual training course, with 1 month of unlimited LEAP time. So this will give you access to 1 week or 5 days of pre-recorded lectures, quizzes, assignments to go through. And then we also have live office hours and live guest lectures every day as well, to kind of help you along and make sure that you kind of, can dive into all the aspects of the technology that you're interested in. And this training course will build up kind of the basic skills needed to successfully build models, so like formulate problems for all of our solvers. And we'll teach you about Ocean, as well as when to use each solver and kind of some tips and techniques for getting good quality solutions back from the solvers. So we have, I think, 5 training courses set up for the next 3 months. And yeah, you can get more information or sign up here or reach out to sales, and we're happy to point you in the right direction or give you more information about what the course entails. Okay, so with that, I will wrap up and open the floor for Q&A.
Great.
So
Thank you so much, Alex. We've answered a lot of questions during the presentation, but we do have some that we have marked to answer live. So here's a question for you. What do the variables here exactly mean? Binary, maximum number of variables in the quadratic equation?
What do the variables mean? I'm not sure if that person's talking about in the code example or.
Well, it was very early on. So it was
okay.
Kind of at the beginning.
Aha, okay. So let me just grab the slide. I'm guessing that it might be related to this.
Right.
So here the variables mean the maximum number of variables for the solver. So for example, CQM can support up to 500,000 binary or integer or a combination of binary and integer. So it doesn't matter what type of variable you're using for a CQM solver, the max of either type or a combination is 500,000. And likewise for the DQM solver here.
Okay. What is the number of partition? What if the number of partitions is variable / to be optimized?
What is the,
what if the number of partitions is variable or to be
what if? Oh, interesting. Yeah, that would be a different formulation. I would have to think about how to formulate that. But that's a really interesting, I think, extension of the graph partitioning problem that we showed today.
Okay. Yeah. How do we estimate the time limit parameter? Is it similar to number of sweeps?
Yeah, good question. So like I said, for small problems, you're probably not going to get a ton of return on increasing that time limit. But for larger problems, it's so problem dependent. What we recommend is starting with the minimum time limit and then, doubling it and seeing, have you started to get better quality solutions? If yes, and if you're happy with that quality of solution, then like maybe you want to leave it there. If not, then maybe you want to double it again. And yeah, just kind of try to find the upper and lower limit of good quality solutions and then kind of scale down to find the minimum time that gives you the quality of solutions you want. But it's very problem dependent. So I don't have a more concrete answer than that.
Okay. By the way, somebody noted in the chat that URL for the quick start doesn't seem to be working. If you send an email again to sales@dwavesys.com, I'll look into it and get back to you. Sorry about that. Alex, is there a resource that shows what can be done with annealing and not with gate-based technologies?
Yeah, also a good question. I don't think we have a single resource, but I do know of a few papers that show how quantum annealing is, currently and likely in the future will continue to be the best quantum technology for optimization problems. So often the gate kind of equivalent of quantum annealing or an optimization algorithm is QAOA. And there are some additional challenges with using QAOA for optimization that annealing kind of circumvents by just the nature of the algorithm. So if you'd like more information, please feel free to email me and I can send you those papers.
Okay, I think we've got time for one more. There's still a lot of questions coming in. The example is about graph operations. Is there anything special about formulating problems as a graph?
Yeah, I think one benefit to formulating problems as a graph is that Yeah, graph problems are just well suited structurally to our hybrid solvers, and can be mapped to the quantum annealer, well, depending on what the graph is. But we have a lot of kind of techniques for doing that. So thinking about a problem and formulating it as a graph is, yeah, like a good sign that it could be a good fit for our system.
Okay, well, I think with that, we're just about out of time. Again, this webinar has been recorded, and in a day or so, it'll be out on the DWave YouTube channel. We do these webinars pretty much monthly. The next one is scheduled for February 23rd, and it'll be a talk by a senior research person at GE, who's going to talk about an application that they've been working on having to do with asset sustainment. So how they kind of manage large products like jet engines and other things to keep them going and optimally maintained. Unfortunately, we cannot record that webinar, but so you'll have to listen to it live, but hopefully you're on our email list. If not, please go to the Contact Us page on our website and we'll add you in. And we thank you so much for attending today. And we hope to see you at another webinar soon.